Select the major product of the following reaction. So you want to take a look and see what we have. So we see that we have an ester, and we are reacting this with two equivalents of a Grignard reagent. So Grignard reagents we know are really strong bases and strong nucleophiles. And this carbonyl carbon of the ester is electrophilic. So to predict the product, I think we should draw the reaction mechanism. So we're gonna go ahead and draw this ester. So there it is. And your Grignard reagent, let me just draw this in a different color. We can assume that this basically reacts as a carbanion. So you can really think of it as being the CH3 minus with the magnesium bromide as a counterion. So the first thing that will happen is this strong nucleophile is going to react with that electrophilic carbon atom of the ester. And so when it does that, it is going to break the pi bond, pushing those electrons up onto the oxygen. So we can draw the product of this first step. So it'll be a tetrahedral intermediate. Okay, so we now have the oxygen has a negative charge. We still have this ethoxy group on the side, and then our new bond is to this CH3 group. And so this is the tetrahedral intermediate. And whenever we have a tetrahedral intermediate, we want to take a look at it and see if it contains a leaving group or not. And this is an ester. And so we saw in a previous chapter that esters do have leaving groups. You can kick off the OR group. So we can have this leaving group here leave. So we're going to reform that pi bond, and we're going to kick off that ethoxy group. And then we can take a look at this. And so we have that benzene ring still, the bond to this carbon. This is now a carbonyl again. And we don't have that ethoxy group. We kicked that off as a leaving group, so we can draw it off to the side here. And we do still have the new bond that we formed in the first step to that CH3 group. So here is that new bond and that CH3 group. And so we want to take a look at what we have now. And we see that we now have a carbonyl with two bonds to carbon, so a carbon on either side. So this is a ketone. And we have more Grignard reagent around. We had two equivalents. And even if we didn't have two equivalents, whatever we did have would react with this ketone. And that's because ketones are more reactive carbonyls than esters. So we have to have two equivalents of Grignard here, just recognizing that as soon as we form any ketone at all, the Grignard is going to preferentially attack that ketone. So let's draw the Grignard reagent again. So there it is, and I'm drawing it as an anion. You could also draw a covalent bond, but I think the anion is a nice way to represent it, to see really where your nucleophilic atom is, that it's the carbon that is attached to that magnesium. So this can add to the ketone, and that will push the electrons up onto the oxygen. And so this is going to give you another tetrahedral intermediate. So you have your benzene ring, this one carbon atom. The oxygen has a negative charge because we gave it an extra lone pair of electrons, and we have now two bonds to these methyl groups because we added one here and a second one in this step. And so we have another tetrahedral intermediate. And so just like before, we want to take a look and see if we have a leaving group. And so we have a bond to carbon, another bond to carbon, another bond to carbon. We don't have a leaving group. So nothing is going to happen here until you add in some sort of proton source. And that's what this second step is. So sometimes we've seen this proton source being H3O+, sometimes we see it as water. So it's just a quench to this reaction. So we have water. And so this alkoxide can grab one of those hydrogens and break that hydrogen-oxygen bond. So hopefully you can see that this is leading us towards D, right? So we've got the benzene ring, the carbon, here's our 2 new methyl groups, and the alcohol that we just generated here. So I don't hold my students responsible for this, but if you're wondering why we're using water instead of an acid in this case, it's because your product is a tertiary alcohol. Because tertiary alcohols are fairly prone to elimination. If you had too much acid, that would be a possibility, so sometimes we just represent this as just water.